In this video, we are going to discuss the fundamental theorem of calculus, which you can guess it's important. Okay, this is the most important tool when we want to compute definite integrals. Okay, so it says that if f of x is a continuous function, then we can compute the definite integral of f from a to b as the difference of capital F of b minus capital F of a, where capital F of x is any antiderivative of the original function lowercase f of x. So what are we saying here? We are saying that to compute the signed area, that is the definite integral between a and b of f of x, it is enough to compute an antiderivative, evaluate it at the extrema of the interval where we are integrating, and taking the difference. So let's see how that works. Let's do an example. So let's say integral from -4 to 2 of x over 2 plus 1 dx. And here f of x is x over 2 plus 1, a equals -4, b equals 2. Okay, so let's apply the theorem. Let's compute the antiderivative first. Find the antiderivative. So let's keep that in mind. Notice that one of the theorem says that this applies to continuous functions. We'll see more about that later. But yeah, x over 2 plus 1 is continuous, so no problem. So find the antiderivative. Capital F of x is the integral from, of x halves plus 1 dx, which we know is x to the power 2 divided by 4 plus x plus c. Okay. Now, here, notice that the theorem says any antiderivative. So the constant doesn't really matter. So we can just not put it. So it doesn't matter in this context. Okay, or in other words, it says any antiderivative. We might as well take something that is convenient for us and make c equal 0. Okay, so we have an antiderivative there. And then the second step, the fundamental theorem of calculus says that the integral of f of x dx is the antiderivative at 2 minus the antiderivative at -4. Okay, f at the ending of the interval minus f at the beginning. And then this is very easy. See what happens. No need to evaluate any rectangles, any limits, nothing. Just take the function that is the antiderivative, evaluate at 2 and -4, take the difference, done. So this is 2 to the power 2 divided by 4 plus 2 minus -4 squared divided by 4 minus 4. And that is, 1 plus 2 minus 16 divided by 4, which is 4 minus 4. This is 0. So we get 3. And that's it. Okay, notice here, this example in particular, x halves plus 1. Okay, so this is an example that we could have done using the definition as area. Okay. So for instance, at 0, it crosses through 1. And then at -2, x over 2 is -1 plus 1, 0. So it's this line over here, x over 2 plus 1. And we are integrating from -4 there we go, from -4, okay, that was not enough, there, to 2. Okay, so we are looking at this signed area. So we have a plus and a minus. Okay, so we can check the computation. Integral from -4 to 2 of x halves plus 1 dx equals the area of the positive triangle. So it's 1/2 times 4 times 2. Okay, the height here equals 2 because you plug in x equal 2 and you get 2 over 2 plus 1 makes 2. And then subtract the negative triangle, which has a base of 2 units and a height of 1 unit. Okay, at -4, we plug in -4 divided by 2 makes -2 plus 1, -1. Okay, so the height is 1, except that it's negative. So that makes 4 minus 1, and we get 3. Oh joy. So we got the same result, so we can have some trust that the method works. Okay, usually when you test a new method, you test it in some function where you can compare with what you were previously using. Here I want to emphasize that the choice of the constant in the antiderivative doesn't matter. Okay. So for example, let's say we have f of x that is equal to x, and we want to compute the antiderivative. And we decide that we want to really keep the constant there and make it super with constant and everything. So we keep it, no problem. Okay, and we try to compute the integral from a to b of x dx. So that will be the antiderivative at b minus the antiderivative at a. So we get b squared over 2 plus c, just evaluating, minus a squared over 2 plus c. And we get b squared divided by 2 plus c minus a squared divided by 2 plus c, sorry, minus c. And you see the constant disappears. We get b squared divided by 2 minus a squared divided by 2. So we might as well take c equals 0 from the start. Okay. So that's the reason why I'm saying it doesn't matter, because once you take the difference, it really doesn't matter.